Imagine a perfectly flat floor, like a giant chessboard. We lay down two number lines across this floor. One goes left and right, and the other goes front and back. They cross exactly in the middle, at a perfect right angle, like the corner of a picture frame. This crossing point is our starting point, which we call the origin, and we label it 0 for both lines. Now, any spot on this floor can be described by just two numbers: how far you walk sideways along the first line, and how far you walk forward or backward along the second. We write this as a pair, like a treasure map coordinate. The first number, the sideways walk, is called the x-coordinate, and the second, the forward walk, is the y-coordinate. The two number lines are called axes. The x-axis runs horizontally, and the y-axis runs vertically. Why do we even bother with this grid? Because it lets us turn a shape, like a curve, into an equation we can work with. Before this, geometry and algebra were separate worlds. The coordinate plane is the bridge. A circle isn't just a round drawing anymore, it becomes an equation like x squared plus y squared equals a number. More importantly for calculus, it lets us turn motion into a picture. Imagine a ball thrown in the air. Its path is a beautiful curve. Its height at every moment is a point on that curve. The steepness of the curve at any point tells us its speed. The area under the curve tells us how far it traveled. Without the coordinate plane, we couldn't draw a function, see its slope, or find the area under it. It is the canvas on which all of calculus is painted. Let's build this grid from scratch. We start with a single horizontal number line. 0 is in the middle, positive numbers go to the right, and negative numbers go to the left. Now, we take a second, identical number line and stand it straight up, crossing the first one exactly at their 0 points. This is the origin. On this vertical line, positive numbers go up, and negative numbers go down. The two axes divide the plane into four regions, called quadrants. We number them counterclockwise, starting from the top right where both x and y are positive. To find any point, you start at the origin. The first number in the pair, the x-coordinate, tells you how far to walk left or right. The second number, the y-coordinate, tells you how far to walk up or down from there. The order is strict, the x address always comes first, just like in the alphabet. Let's solve a real problem. Imagine a map where each unit is 1 kilometer. City A is at coordinates 1, 1. City B is at 4, 5. We want to find the straight line distance between them. On our grid, we can draw a right triangle. The horizontal leg goes from x equals 1 to x equals 4, which is a length of 3. The vertical leg goes from y equals 1 to y equals 5, a length of 4. These two legs meet at a right angle. The straight line distance we want is the hypotenuse of this triangle. The Pythagorean theorem tells us that the square of the hypotenuse is the sum of the squares of the other two sides. So, 3 squared plus 4 squared equals 9 plus 16, which is 25. The distance is the square root of 25, which is exactly 5 kilometers. This method works for any 2 points on the plane, and it's the foundation for the distance formula you'll use constantly in calculus. A point is simply a precise location on the coordinate plane, like a dot on a map. We describe that location with an ordered pair of numbers, written as x, y. The first number, x, tells you how far to walk left or right from the origin along the x-axis. The second number, y, tells you how far to walk up or down parallel to the y-axis. Plotting just means marking that exact spot on the paper. The scale is the ruler we draw on each axis, the markings that tell us what each step is worth, like 1 box equals 1 unit or 1 box equals 10 units. Why do we bother plotting points? because it turns abstract equations into pictures we can actually see. Imagine you have a rule, like the temperature of a cooling cup of tea over time. You can write it as an equation, but if you plot a point for each minute, you get a curve that shows the whole story at a glance. In calculus, we are always studying how one quantity changes with another, like speed changing with time. Plotting points is the very first step to building those graphs, and getting the scale right is what makes the picture accurate and useful. Here is how you actually do it. First, look at the scale on both axes. The scale tells you what one box or one mark is worth. Often it is 1 unit, but it could be 2, 5, or even 100, depending on the numbers you need to show. A point is always written as an ordered pair, so the order matters. The first number is the horizontal distance from the origin, and the second is the vertical distance. To plot the point 3, 2, you start at the origin. You walk 3 steps to the right along the x-axis, because the x value is positive 3. From that spot, you walk 2 steps straight up, because the y value is positive 2. You mark the spot with a dot and label it with its coordinate so you do not forget what it represents. Let us solve a real problem. Imagine you are tracking a car on a map. The car starts at the origin, which we will call the parking lot, at coordinates 0, 0. It drives in a straight line to a shop. The shop is 4 kilometers east and 3 kilometers north of the parking lot. Our scale is simple, 1 unit on the graph paper equals 1 kilometer in the real world. To plot the car's path, you first mark the starting point at the origin. Then, you plot the shop's location. You walk for units to the right along the x-axis, and from there, 3 units up. You mark a dot at 4, 3 and label it. Finally, you draw a straight line connecting the 2 points. That line is the car's route. The same method lets you plot any journey, any shape, or any data on a graph. When you draw a graph on the coordinate plane, it will often cut through the x-axis or the y-axis. The spot where it touches or crosses an axis is called an intercept. An x-intercept is any point where the graph hits the x-axis, which means the y-coordinate there is exactly 0. A y-intercept is where it hits the y-axis, so the x-coordinate is 0. For a function, we give the x-intercept a special name, a root. It is the input value that makes the output 0. So intercepts are simply the graph's meeting points with the axis, and roots are the x values that make a function equal to 0. Why do we care so much about where a graph crosses the axis? Because in real problems, 0 often means something important. If you are tracking profit, the x-intercept is the break-even point where profit becomes 0. If you are measuring height, the root is the moment the object hits the ground. Intercepts also split the graph into positive and negative regions, which is crucial for understanding inequalities. In calculus, finding roots is the first step to solving equations like where is the slope 0, or where does this curve change sign. So intercepts and roots are not just dots on paper, they are the answers to when does something become nothing. Finding intercepts is straightforward because we use their definitions. To find an x-intercept, we know the point lies on the x-axis, so its y-coordinate is 0. We substitute y equals 0 into the equation of the graph and solve for x. To find the y-intercept, we know the point lies on the y-axis, so x equals 0. We substitute x equals 0 and solve for y. For a function written as f of x, the roots are simply the solutions to f of x equals 0. This turns a visual question into an algebra problem. For example, if a line has the equation y equals 2x minus 4, setting y to 0 gives 0 equals 2x minus 4, which solves to x equals 2. That is the x-intercept. Setting x to 0 gives y equals negative 4, the y-intercept. Let's use this idea. Imagine you throw a ball straight up. Its height above the ground in meters after t seconds is given by h of t equals negative 5t squared plus 20t. We want to know when the ball hits the ground. The ground means the height is 0. So we set h of t equal to 0. That gives negative 5t squared plus 20t equals 0. We can factor out a negative 5t, leaving t minus 4. So either negative 5t equals 0, giving t equals 0, or t minus 4 equals 0, giving t equals 4. T equals 0 is the moment you throw it, so the meaningful answer is t equals 4 seconds. The ball lands after 4 seconds. The root of this function told us the landing time. This same method finds break-even points, or when a moving object passes a marker. Imagine you're walking up a hill. Some hills are gentle, some are really steep. Slope is just a number that tells you how steep a line is on a graph. It's the same idea as the rate of change, how fast the y value climbs or falls when you take a step to the right along the x-axis. Think of a staircase. If each step takes you a long way forward but only a little bit up, the staircase isn't very steep. If each step shoots you high up but barely forward, it's super steep. That's all slope is measuring. So why do we care about steepness? Because in real life, we constantly ask, how fast? How fast is a car speeding up? How quickly is a phone battery draining? On a graph, the slope answers that question. If you plot distance against time, the slope is your speed. If you plot money saved against weeks, the slope is your savings rate. It lets you predict what happens next. If you know the rate, you can extend the line and see the future. This idea is the very first step toward calculus, where we learn to find the rate of change even for curvy, non-straight lines. Let's see where the formula comes from. Take any straight line on the coordinate plane we learned about earlier. Pick 2 points on it, any two, it doesn't matter which, because a straight line is equally steep everywhere. Look at the vertical change between them, that's the rise, how much the y value goes up or down. We find it by subtracting the first y from the second. Then look at the horizontal change, that's the run, how much the x value moves forward. We find it by subtracting the first x from the second. The slope is simply the rise divided by the run. We often use the letter m for slope. If the line goes uphill left to right, the rise is positive and the slope is positive. If it goes downhill, the rise is negative and the slope is negative. A flat horizontal line has 0 rise, so its slope is 0. Let's solve a concrete problem. Imagine you're building a wheelchair ramp. You've plotted the start and end points on a graph, where the x-axis is the horizontal distance from the wall and the y-axis is the height. The start is at the point 1, 2, meaning 1 foot out and 2 feet high. The end is at 4, 8, meaning 4 feet out and 8 feet high. The rise is the change in height, 8 minus 2, which is 6 feet. The run is the change in horizontal distance, 4 minus 1, which is 3 feet. The slope is the rise over the run, 6 divided by 3, which equals 2. This means for every 1 foot you move horizontally away from the wall, the ramp rises 2 feet. That's a very steep ramp. The same method works for any 2 points on any straight line, just find the rise and the run, and divide. Imagine you're walking along a path shaped like a smooth hill. You climb up, reach the very top, and then start going down. That top point is a maximum, the highest spot on that part of the path. If you were in a valley, the lowest point before you start climbing again is a minimum. On a graph, these special points are called turning points, because that's exactly where the curve turns around. The slope, which we already know as the rate of change, is 0 right at these points. The path is flat for just an instant before it changes direction. Why do we care about these peaks and valleys? Because in real life, we often want to know the best or worst case. A business wants to find the price that gives maximum profit. An engineer designing a bridge needs to know the minimum strength required so it doesn't break. A farmer might want to find the maximum area they can fence with a fixed amount of wire. All these questions, when is it biggest, or when is it smallest, are answered by finding the turning points on a graph. They show us the extreme values a situation can reach. Let's see how this works using the idea of slope we already know. Picture a curve that goes up, flattens at the top, and then goes down. As you walk up the left side, the slope is positive, you're climbing. Right at the peak, for a single instant, the ground is flat, the slope is exactly 0. Then as you walk down the right side, the slope becomes negative. So a maximum is a point where the slope changes from positive to negative, passing through 0. A minimum is the opposite, you walk down a slope that's negative, hit a flat bottom where slope is 0, and then climb up a positive slope. The turning point is simply the spot where the slope equals 0 and the curve changes its direction. Let's solve a concrete problem. Imagine you throw a ball straight up. Its height above the ground over time makes a curve on a graph, it goes up, reaches a peak, and comes back down. Suppose the height in meters is given by the expression 10t minus 5t squared, where t is the time in seconds. We want the maximum height. At the peak, the slope of this height graph is 0. The slope here is the rate of change of height, which is the ball's upward speed. At the very top, the ball stops rising for an instant, its upward speed is 0. That happens when the slope expression, 10 minus 10t, equals 0. Solving that gives t equals 1 second. Plug t equals 1 back into the height expression, 10 times 1 minus 5 times 1 squared, which is 10 minus 5, giving 5 meters. So the ball reaches its maximum height of 5 meters after 1 second. Imagine you're holding a bendy piece of wire. You can curve it so it makes a little bowl that could hold water, that's what we call concave up. Or you can flip it over so any water would spill out, that's concave down. Concavity is just the name for which way the curve is bending. And right at the spot where the bend switches from holding water to spilling water, or the other way around, we call that an inflection point. It's the exact moment the curve changes its mind about which way to cup. You already know how to find where a graph turns, its maxima and minima. But two graphs can have the exact same turning points and still look completely different between them. One might swoop up gently, another might dive down and then shoot up. Concavity is what captures that hidden shape. It also gives you a powerful test. If you're at a flat spot where the slope is 0, and the graph is concave up, you're in a valley, a minimum. If it's concave down, you're on a peak, a maximum. So concavity doesn't just describe the bend, it helps you classify the turning points you've already found. We already know the first derivative, f prime of x, tells us the slope or rate of change at any point. Concavity comes from asking, how is that slope itself changing? If you're walking along the graph and the slope is getting steeper and steeper upwards, the curve is bending up, that's concave up. That means the derivative of the slope, which we call the second derivative and write as f double prime of x, is positive. If the slope is getting more and more downhill, the second derivative is negative, and the curve is concave down. So concavity is just the slope of the slope. An inflection point is simply where f double prime of x crosses 0 and changes sign, the slope stops getting steeper and starts getting shallower, or vice versa. Let's make this concrete with a car on a straight road. Suppose the car's position over time is given by a cubic function, f of t equals t cubed minus 3t squared plus 2t. The first derivative, f prime of t, is the car's speed. The second derivative, f double prime of t, is its acceleration, how quickly the speed is changing. Let's find where the acceleration is 0 to locate an inflection point. We compute f double prime of t equals 6t minus 6. Set that to 0, 6t minus 6 equals 0 gives t equals 1 second. Before t equals 1, say at t equals 0, f double prime is negative 6, the car is decelerating, its speed is decreasing. After t equals 1, say at t equals 2, f double prime is positive 6, the car is accelerating. So at exactly 1 second, the car switches from slowing down to speeding up. That's an inflection point in the position graph. Imagine a graph that runs off toward the edges of the coordinate plane, getting closer and closer to a straight line, but never quite landing on it. That line is called an asymptote. The word comes from Greek, meaning not falling together. The curve and the line are forever chasing each other but never meet. It is like a ghost boundary that the graph can approach but never cross. You have already seen how graphs can turn and bend. An asymptote is a different kind of guide. It tells you where the graph is heading when it goes out to infinity. Why do we care about a line the graph never even touches? Because an asymptote answers a very practical question: what happens in the long run? Think of a car accelerating. Its speed cannot go to infinity. Air resistance and engine power create a top speed, a horizontal asymptote on a speed-time graph. Or think of the cost per item when you mass-produce something. The more you make, the closer the cost per item gets to the raw material cost, but it never drops below that. Asymptotes let us read the ultimate destiny of a process directly from the graph, without needing to calculate every point. They are the graph's way of telling you its final story. Let's see where asymptotes come from, building on the idea of slope and intercepts you already know. Take a rational function, which is just one polynomial divided by another. A vertical asymptote happens where the denominator equals 0, because division by 0 is undefined and the graph shoots up to infinity or down to negative infinity. For example, in 1 over x, the denominator is x, so x equals 0 gives the vertical asymptote. A horizontal asymptote is found by asking, as x runs off to positive or negative infinity, what value does y settle toward? For 1 over x, as x gets huge, 1 over x gets tiny, approaching 0. So y equals 0 is the horizontal asymptote. If the numerator's degree is exactly 1 more than the denominator's, you get a slanted asymptote, which we find by polynomial long division. The key is that the asymptote describes the graph's behavior at the extremes, not in the middle. Let's solve a concrete everyday problem. Suppose you start a t-shirt business. You pay a fixed setup cost of $100 for the screen printing equipment, and each shirt costs $5 in materials. You want to know the average cost per shirt if you make X shirts. The total cost is 100 plus 5x. The average cost per shirt is the total cost divided by the number of shirts, so the function is y equals 100 plus 5x, all over x. Let's find the horizontal asymptote. As x gets very large, meaning you make thousands of shirts, the $100 fixed cost is spread so thin it becomes negligible. The average cost approaches 5x over x, which is 5. So y equals 5 is the horizontal asymptote. This tells you that no matter how many shirts you make, the average cost per shirt will never drop below $5. That is the long-run boundary set by the material cost. Imagine you have a wavy line drawn on graph paper. That's your curve. Now pick 2 points on the horizontal x-axis, say x equals 1 and x equals 4. The area under the curve is all the space trapped between that wavy line and the flat x-axis, from your left point to your right point. Think of it like the amount of paint you'd need to color in that region. If the curve goes above the x-axis, we count that area as positive, like land above sea level. If it dips below, we count it as negative, like a hole you dig out. So the area under a curve really means the net space, adding the bits above and subtracting the bits below. Why do we care about painting the space under a curve? Because it answers real how much questions that simple multiplication can't. Suppose you have a speedometer graph that curves up and down as a car speeds up and slows. The area under that speed curve between two times tells you the total distance traveled, not just speed at one moment, but the whole journey. Or think of pushing a swing, the force you apply changes as the swing moves. The area under a force against distance curve gives the total work you did. This idea is the seed of integral calculus, the branch of maths that adds up infinitely many tiny pieces to find a whole. It's the flip side of the slope and rate of change ideas you already know. So how do we actually measure this curvy area? We can't just use length times width, because the top edge isn't straight. The trick is to slice the region into lots of very thin vertical strips, like cutting a loaf of bread. Each strip is almost a rectangle, its width is a tiny step along the x-axis, and its height is the curve's value at that spot. The area of one strip is just height times width. If we add up the areas of all the strips, we get a pretty good guess for the total area. Now here's the magic: as we make the strips thinner and thinner, so thin they're practically lines, our guess gets better and better, until it becomes the exact area. This process of adding up infinitely many infinitely thin slices is what we call integration. Let's put this to work with a real problem. A car starts from rest and speeds up steadily. Its speed at time t is v of t equals 2t. So after 1 second it's going 2 meters per second, after 2 seconds 4 meters per second, and so on. The graph is a straight line sloping up from the origin. We want the total distance covered in the first 5 seconds. That distance is exactly the area under this speed line from t equals 0 to t equals 5. Look at the shape, it's a right triangle. The base along the time axis is 5 seconds. The height at t equals 5 is 2 times 5, which is 10 meters per second. The area of a triangle is half the base times the height, half of 5 times 10, which is 25. So the car travels 25 meters. This triangle method works for any straight line speed graph. The area is always half the base times the height.